I welcome you the NPTEL course on earthquake resistant design of foundations. And this is the 30th lecture on this course, and we are going to talk about well foundation, which is basically the fourth module of this course. And within the well foundations, what we are going to talk is, these are the listed topics. Introduction, which we have already discussed. Lateral stability of well foundations, that has been also over. Then construction and sinking of a well, also discussed. Today, first we are going to talk about tilting and shifting of wells. And once we are done with that, then we will be discussing two numerical problems on well foundations, which will be covered based on Tagi theory as well as IRC method, where in IRC method we are going to discuss both elastic theory method as well as ultimate soil resistance method in numerical problems. So let's start with the tilting and shifting of wells. That when this is very important, that if the well should be straight, so it is safer and economical to avoid tilting and shifting of wells by adopting the following preventive measures. The first, the outer surface of the well curve and staining should be level, straight, and smooth. The radius of the well curve should be kept 2 to 4 centimeters more than the outer radius of the well staining. So you have two issues. One is called well curve and another is staining, that we have also discussed earlier. The cutting edge should be sharp and of uniform thickness. The staining should be built in lifts and the entire staining height should be built in one straight line from bottom to top at right angles to the plane of the curve. Dredging should be uniform on all sides of the well. For a twin well, dredging should be uniform in both the wells. Then the well should be constructed in stages of small height increments. That means rather than constructing one time, it is required to be constructed in increments, as we discussed earlier. The magnitude and direction of sinking of wells should be properly and carefully monitored on a continuous basis to identify any tilt or shift and adopt appropriate corrective measures immediately to rectify the same. If the well shows a tendency for tilting, dredging should be done on the higher side. And if this doesn't bring the required improvement, sinking should be stopped and should be resumed only after the tilting is corrected. Okay. Then dredge material should not be deposited unevenly around the well. When a net dredge is used to provide additional sinking effort, it should be placed evenly on the loading platform. So the tilting and shifting of wells are explained using these figures also. So let me share with you before I go. This is here. You have a well. Let's say it is inclined. So excavation should be done on higher side. Then here you could see in the figure B. This is plumb. So using that, this is inclination of this well is measured with respect to vertical, and you can see to correct this one naturally. If you tilt this portion on the left hand side, then this tilt will be corrected. So idea is that here you put this some pulley and loading arrangement to try to bring this in this direction. Then you have the rope and hook also. Then you have rolled steel joist. All these issues are there. So these are means to correct the tilting here. So the sandbags are used normally here to apply the loads, or some jacks are applied here. What you have here. So now the issue is here. How you can rectify tilting and shifting. Suppose there is some issue with tilting and shifting, then it can be rectified. First, continuous monitoring should be done to identify if any tilt or shift of the well occurs, and in that case, following measures should be adopted as deemed appropriate as per the decision of the engineer in charge. So first is controlled dredging should be done more on the higher side, that is on the opposite side of the tilt, as shown in figure A. This method is helpful only in the initial stages of well sinking. Eccentric loading is applied by using extra downward pressure on the higher side, as shown in figure B and C. So what is shown in the figure B and C, in that case, extra should be applied. Now continue with that. What you have, then pulling the well from the higher side in the opposite direction, the tilting is also effective in rectifying it. So that means you need to pull it in opposite direction The pull can be applied by winding steel wire around the valve through an anchor. Wooden sleepers are used during pulling to avoid damage to the valve string, as shown in figure D. The pull can also be applied by using an anchor below the cutting edge on the higher side, which is shown in figure E. Then push can be applied to the valve from the lower side to rectify the tilt. Care should be taken so that pulling or pushing doesn't cause a shift of the valve. Water jets will be used on the higher side near the bottom of the valve to remove the soil partially, thereby reducing the frictional resistance on the higher side. So you have here, like these are in figure A, B, C, and what is done in D, sleepers are used here to rectify the tilt. This is tilted this side, so this need to be pull it down like here, and then bring it this side. Same thing is here. Some anchor is used here with below the valve curve near valve curve, and anchoring with the pulley, and then it is trying to fix it. There is tilt, so idea is to push this side in such a way on the right side, so that this tilt can be corrected. Then sometimes netlays are used. That is the basically netlays are the group of sandbags and other things. So they are using on the top of this. This is used on the top of this valve, and then it can be corrected. So this is about tilting and shifting of valves. Now what you have, let's discuss some numerical example on this valve foundations. So the first numerical example is on a circular valve of 4.5 meter external diameter and 0.75 meter staining thickness. It is embedded up to a depth of 12 meter in a uniform sand deposit. The angle of healing distance of sand and the submerged unit weight are given 30 degree and 1 ton per meter cube respectively. The valve is subjected to resultant horizontal force of 50 ton and total moment of 400 ton meter at this core level. So it is subjected to horizontal force as well as moment. Both are given here. Assuming the valve to be a light valve, compute the allowable total equivalent resisting force due to earth pressure. Okay. Then factor of safety of 2 may be adopted for soil resistance. Determine the magnitude and point of maximum bending moment in the valve string. What will be the change in computed values for a heavy valve when the valve is assumed to rotate about the base? For the heavy valve, the point of rotation can be assumed at the valve base. So this need to be done using what is called Tagi's theory, and this various formulations are listed here. First of all, because here both moment as well as the horizontal force is given, so you can find the application of horizontal load is applied at a height h, which is given by m by q, so it comes out to 8 meter. So the point of application of horizontal load above is called level 8 meter. Total height h will be h plus b, that is 8 plus 12 meter, 20 meter. And from equation 17 points, like you have this, already discussed this equation, we have discussed in theory. So using this equation, what you can find, the value of d1 twice d1 can be calculated from this relation, where 3h1 is 20 meter, 9h1 square minus 2d, 3h1 minus, where d is the depth of the valve. D is not the diameter of the valve, rather capital D is the depth of the valve. So once you substitute these numbers here, then you find that d1 is 5.26 meter here, positive sign. Then we can find the value of Q max. And for phi equal to 30 degree, the value of active earth pressure coefficient is 1.33, while it is opposite, that is 3 for passive resistance. Now in this case, for a light valve with rotation above the base of the valve, the value of Q max can be determined from this relation, where Q max is half gamma d Kp minus Ka into d minus twice d1. So in this case, what you can have, that is the maximum value of Q that can be calculated from this relation. And gamma, because here unit weight is given, but it is saturated, so it is given, unit weight is given to you in this question, 1 ton per meter square, submerged unit weight. So because for the saturated state, gamma should be submerged unit weight. So gamma is 1, d is 12, and 3 minus 0.33 divided and multiply by B minus twice D1, where D is 12 and D is 2 into 5.26. So with that Qmax, you can find the value, which is 23.68 ton per meter land. And once this Qmax is known, then allowable load QA can be calculated as a Qmax into L divided by F. So that means where total multiple, this was for per unit length, so multiply by the length, this is L is given 4.5 meter, and the factor of safety is given 2. So once you work on this, you get the allowable load as 53.28 ton. So the allowable load in this case as 53.2 ton. Now this was the case when you are considering that well is not heavy well. Now for this case, the point of maximum bending moment will be at the location where the shear force is 0, and let the point 0 shear to be at x meter below scour level. Then the value of x can be found from this relation of gamma and x square into L by F into K minus K equal to Q. So with that, you can calculate the value of x, and x can be calculated from this equation because all things are known here in this equation. And once you put the number gamma L Kp minus, so you get x equal to 4.08. Once x is known, this is the point of zero shear force, then maximum bending moment can be found Q into H plus x minus Q into x by 3. So this was the case here. So once you solve it, then you get QH plus twice Q x by 3. And once you put the number here, 50 into 8 plus 2 into 15, so you get 536 ton meter. So this was the case. Maximum value of bending moment for this case is 536 ton meter. For heavy well, if we consider instead of light well, the well is heavy. In that case, Qmax can be calculated directly from this relation Kp minus Ka dq h plus p, and in this case, d1 is not required. So you have this here. Once you put the number Qmax, so you get the value 38.4 ton per meter, and allowable load will be 38.4 into 4.5 divided by 2. This is the, and once you have this, you obtain 86.4 ton, the value of Qmax for heavy load. Now you could see this was the case, allowable load 86 was the case when you have the for heavy weight. But earlier for QA you have got 53.28 ton. So that means for reached case, when you assume that point of rotation will be not at some height, rather it is at the base. In that case, the allowable soil pressure QA will be higher. This is 86.4. This value was 86.4 ton. Which is increased now. And the earlier value which you have shown is 53.28. There is a lot of difference. So in this answer, you get that this is higher value and which was expected. Why it is higher? Because the rotation, the well being reached and rotation is assumed at the base of the well. So this method was when what is called IRC method, and for the solution of well formation. Now let's discuss the second method. Last one was Tagi's method. Now let's discuss IRC method. In IRC method, you have two issues. One is related to elastic theory method. Another is called ultimate solutions method. So let's discuss example 2. And in this example, following data are given to you for a single line railway bridge. First is net downward load on well including surf rate. This is given 1400 ton. Horizontal force at scar level is also given 200 ton. Moment at scar level 4150 ton meter. And depth of well below scar level is 15 meter. Saturated unit weight of sand is 2 ton per meter cube. Angle of seeing in resistance of soil is 35 degree. While angle of wall friction is 20 degree. External diameter of well is 8.5, while internal diameter is 5.5. And allowable bearing pressure is 55 ton per meter square. This is also given. Now, we need to check the lateral strength of the well as per the procedure laid down by the IRC 45, which is published in 1970. So let's understand what is elastic theory method. In elastic theory method, that you don't allow the yielding. Here, what you have projected width of valve, first of all, L is 0.9 times B, where B is the width of the valve. This is coming to 8.5, so you got the value of L, 7.665. Then the moment of inertia, IB, is calculated using this relation pi d4 or 64. Once you put the number, then you got to 56.2. Now the value of I, which is given from this relation, is IB plus MIB 1 plus twice mu prime alpha. Here, assuming that the ratio of horizontal mode and vertical mode, arc ratio coefficient Ks is same, so ratio Kh and Kv is 1. Once we assume here number 1, the second thing, the mu prime is given by 10 delta, which is 1020 degree, 0.364, and the value of alpha is also given, which is 0.18. And alpha is calculated from B by pi d. Like B is 8.5 meter, but D is also quite high. So you end up with the value of 0.18 for alpha. The value of IV is also coming in this equation, and IV is given by the relation LDQ by 12, and which is given from this relation. You got the number 2151.56, and now you substitute all values in these equations 1, which is for IV here. So find the value of IV, which is you put here I equal to IB, which is 56 point, M is 1,215, and then you put the value of IV, and finally in the bracket, you need to understand mu prime is here 0.364, okay, which is equal to 1020 degree as listed here. So once you put all the numbers, then I comes out to be here 2690.33 meter 4. So this was the value of I, and now we use this I for further calculation. Let's say radius R, which is D by 2 into IMIB. So once you put the numbers, then so D equal to 15, which is not depth of the valve, 15 meter, over 2, I and MIB is also given. So in that case, you can have this radius equal to 9.38 meter. Now we are done almost with this. So we go in the construction mode. So first check which need to be applied for elastic theory method, that the value of H should be greater than M by R 1 plus mu prime minus mu. Mu is Poisson's ratio for the solid, and mu prime is also 10 delta, which is like you know that mu prime is here given to you 10 delta. So using this, once you put the number, H comes and that means on the right hand side, M by R 1 plus mu. So here you see, once you put all the numbers, mu equal to mu prime is 1020 degree, while mu is 1035 degree. Putting all these numbers in this equation, you get minus 425.09. Oh, okay, this is negative value. So this value should be this H here, H should be greater than that. Now the value of H, which is given in the equation, is 200 ton. Horizontal forces is column. So naturally, 200 ton, it will be higher than what you have this negative minus 425. So as a result, we can say that this check is satisfied. It is fine. Another check is also applied between H and M by R. So what you have this check, that the value of H should be less than this value which is listed here. Again, you put the numbers, all the numbers here in this equation, and once you put the numbers 1 minus 10, 35, 10, 20 degree and all, then you end up in the value 1086.47, and this value, which is should be the condition that should be less than H, because H is 200 ton, so this is obviously fine. So this is not an issue. Now to check the elastic state, the mm divided by I, that is mass moment of inertia divided by I, should not be greater than gamma into Kp minus Ka. This quantity should not be greater than. That means this quantity should be less than this value. So what you have, Kp in these equations is nothing but 1 plus sine phi, 1 minus sine phi. So you get this for 35 plus phi. Same thing is for Ka, which is reverse of 1 over Kp, it's 0.271. So this way you got these numbers, and when you put in this equation, that is mm by u, so you could see here in this identity. So left hand side is 1.54 and right hand side is 3.417. So you can conclude that this number is also less compared to when we solve this. So that means this is 7. Now this was for elastic theory. Continue for elastic theory method. The last item, the check of stresses. Two stresses sigma 1 and sigma 2 are given in this relation here. W by A minus mu prime P plus M by 2. So once we put the numbers in here, again you got this 21.83 plus minus 6.56, because there is plus minus sign is coming. So the positive value here will give you 28.39, while the negative value will lead to you 15.27. And both sigma 1 and sigma 2 are checked here. Sigma 1 should not be greater than 55 ton per meter square, and sigma 2 also. Then, and you have some tension, but this tension in the road is very limited. That is 6.5, almost 7% only. So that is another view. So what do you have here? That means if you have here using this, two quantities are there. So sigma 1 is greater 28.39, but this quantity is less than 55 ton per meter square, which is the permissible value. So this is fine. Same thing is for sigma 2. Here it should be sigma 2. Sigma 2. This should be sigma 2. Sigma minus. Okay. So this correction need to be done. Now let's discuss another method, or ultimate resistance method from IRC only. First one was IRC elastic theory method, and the second one is ultimate resistance method. In this method, the soil pressure W by A should be within the permissible limit of the bearing capacity. So what do you have in this case? You could see that the value of W by A is coming 24.57, and it is not greater than 82.5 ton per meter square. Therefore, it is set. Now continue with that. The moment at the base, MB can be calculated using this relation QWB and pi. So in this case, once you put the number, first of all, this coefficient Q, this depends on the shape and the d by v ratio. So d by v ratio in the given problem is 15 divided by 8.5, almost 1.75. So once you have this d by v ratio, for this d by v ratio, you can calculate the value of Q. So this is here, the d by, and then because you have this number 0.53, so it will be in between 1.5 and 1.2. So this you get this Q equal to 0.53 for this value of d by 1.75. It will be average of this. And once you put the number here, 1400, 8.5, and 35, so you got 4,416.2 ton per meter. So that is for this moment is for the case when you have applied this correction. Now coming to this MS and MF that is listed here, and this first MS is here. So what you have? Okay, so this is total M basically. This should be not there. The MF is coming here. So what you have, the value of MS is calculated from this relation, where gamma is also different, and once you put these numbers, then you got Kp minus K and all these things. So 8,827. Then in the second case, for frictional case, this is given by from this relation, and the number is coming from. So ultimately, total resistance M 0.7 times of MB plus MS plus MF. And once you put inside the bracket, so you get 10,734.28 ton meter, so which is greater than 4,150 mm. So this is should be all. This is all right because the value of MS, this MR, should be less than the load coming from the superstructure. So this condition is already satisfied here. So this was the about ultimate solution. So thank you very much for your kind attention. These are the references, two references. One is book by Gopalaganjan Rao on soil materials. So this is easily, then you have the BIS code, which is related to design and construction of well foundations. Thank you very much.